Thank you, Marcelo. Thank you to all of the organizers. As it was repeated many times, I'm most honored and happy to be here. Having been here, I cannot remember all of the lecturers of that school, but 3 of them were Helena Speck, which later received the Nobel Prize, Ray Laflamme, who did a lot of work on NMR and unfortunately died this year after a long fight with cancer. And Alan Cabello, who's also another fan of this conference, has been here many, many times. I hope you also become fans of this conference. I always found that it's a very nice and interesting place to, as Marcelo said, not only learn and discuss lots of physics, but also make friends and networking. I think most of my colleagues with whom I interchange and I think about physics, I learned here, I got to know here, discussing physics in this hall. Well, not in this hall. Formerly, this event was taking place in downtown in a place called Casa. Now it takes place in this beautiful hotel. The hotel was very nice, by the way. And also drinking beers and staying until night, partying. And I don't know if you still rent a big house. The Brazilians that come together. No, that doesn't happen anymore, right? There was I think so yeah. You can ask me about that anyway. Good. So, I will be posting the slides online. Is that who you are? If you'd like to download the slides and take notes on them, you can scan that with your camera. Now they're only the slides of today, tomorrow the ones of tomorrow, and so on and so forth. So you can get them there. So the title of the series of 3 talks that I will begin is How to Twist, Turn, and Kick Ions Using Structured Light. I am a professor and researcher at the University of Buenos Aires, as I said, and before starting, I would like to also tell you a little bit about myself. So I did my undergraduate at the University of La Plata in Argentina. And when I was finishing, I was presented by a professor the experiment of interference of very big carbon molecules. Oh, okay, sorry, that was a bit too far away. Very big carbon molecules, something is called Bucky spheres. And I was most astonished that you can actually see quantum interference with very big objects. And that's how I got into quantum, and I wanted to do quantum experiments. So I did a PhD in quantum information with photons, and that's where I started to connect with the Brazilian community. We did our experiments in Buenos Aires, starting up a lab with a lot of help from the Brazilian community. And then I moved on to Germany to specialize on trapped ions. I will be talking especially about trapped ions on the lecture tomorrow. And after that stay, I came back to Buenos Aires, went back to Buenos Aires, where I started the Cold Ions and Atoms Lab. The team there, you can see here, so there's a couple of, so it's me and an associate researcher, a postdoc, Nico, who did his doctoral work there, and there are 3 PhD students which are here. That's Sandy, Cory, and Caro, who are sitting around there. So you will get to meet them, get to know them. And in the group, we work a lot still with a lot of collaborations with our theory friends from Buenos Aires, and also with our collaborators in Germany, where I did this postdoc stay. I still work a lot. So what I will be telling you about is one of the 2 main interests that we work in the lab. So there's 2 main lines of research. One is about quantum optics with structured light beams. So that's the interaction of light, which is structured, which is not spatially homogeneous over atoms, with single atoms. And the other research topic, which I like a lot, but I won't be talking anything about it on this conference, or on this school. I will be talking about it on the conference, so if you stay for next week, I will talk about that. And if you're interested in any break, come to me, I can tell you a little bit about it. And actually, we're looking for a postdoc in this project. We have money for a postdoc in this project, which is optical cooling of solids. So we are extending the techniques of Doppler cooling, sideband cooling, optical cooling from the atomic regime, where you can only cool very dilute gases, to the solid state regime. But as I said, this series of topics will be more about the research topic that I've been working on for the last I would say 15 years, which is actually a question that came out, I'll jump through this and go back to it, which came back, which started actually in one conference, a school very similar to this one, but one that happened a little bit before the one that I came, which was a school that was held in Sao Paulo in 2008. It was a Schmiegelow school. And at the Schmiegelow school, there were two professors lecturing. One of them, some of you might know, that's Paraty, who's a researcher at Rio de Janeiro, and another one was Schmiegelow, who was lecturing about trapped ions. So Schmiegelow was telling us about how you can trap. This is an image of a trapped ion in our lab, and what you see around it is a trap. The trapped ion is that little dot in the middle. And he was telling us about how you can trap and you can cool, and I will tell you about that tomorrow. So we will discuss trapped ions tomorrow. And at the same time, Paraty was discussing about how you can generate and structure and store information and transmit information in structured light beams. So beams that are not a Gaussian beam, or that you cannot think about them being uniform over an atom, but that they have some structure, like this donut light beam. And the question that came around that we were discussing in coffee breaks and so on is, okay, what would happen if you would place a single trapped atom or a single trapped ion in the center of one of these beams? And if you look at the typical size of this thing, so if you focus a beam down to the diffraction limit, that the best you can do if your beam is around in the visible regime, you will do a focus size of 1 micron. That's if you're doing things very good. If not, it will be quite bigger. And a trapped ion in a harmonic trap typically has wave packet sizes around 60 nanometers. So that's very small with respect to the size of the beam. So the immediate answer that came to my head and to the head of many of us who are there sitting now is like, of course, nothing will happen. But fortunately, there's much more to ion-like interaction with just intensity, and I will guide you through this in the series of lectures that we'll be doing the next 3 days. And I hope to keep you awake. So all of them will be, I'm always the last to speak in the evening. So I hope you stay for that, and then we will go over beer, discuss more physics and so on. So how are these lectures structured? So today I will be talking about the basics of structured light. So I will be talking all about results which are theoretically and experimental, but not mine. To do a little bit of a screen over, a look over on the basic physics behind that. Tomorrow we will start with structured light interacting with atoms, and we will be mainly looking at what happens with the valence electrons of those atoms. So the atoms as a more or less fixed thing in space, but its internal part can change because of the structure of the beam. And on the third lecture, I will tell you how you can also start to move those atoms around. So how the movement of the center of mass of these atoms can also be influenced by the structure of light. So if I manage to go through all of this today, I will go through a small motivation, a brief history of light and matter interaction, a little bit about Gaussian structured beams, algorithm momentum of light, beyond the fraction approximation. This topic will probably have to jump, because I think we won't get enough time, and I will tell you a little bit about how to generate these beams. So, without further ado, let's jump into part one. So, the discovery that light had many interesting characteristics apart from its color came already in the 19th century. Some of the results which I think are important and nice are enumerated here. So people knew that there were some things called polarizers. There were crystalline polarizers. They were called, they had funny names that we now know as calcite, but like they were called like Espato de Islandia, or island spade. Some kind of stone that you could find in Iceland. That's what we call calcite. That's a typical birefringent stone that you would know separate one polarization from the other one. And after that, people realized that there were some other materials that would do some funny things, like rotate the polarizations. You could rotate the polarization in quartz crystals, also in organic chemistry. And Herschel in 1820 discovered that there was something called like quartz and anti-quartz. So there was one quartz that would rotate the polarization in one direction, and another quartz that would rotate the polarization in another direction. And that led to Pasteur and Van Hoff and also Level a little bit later in the 19th century to discover that there were actually organic molecules that would also do this right and left rotation, like fructose and sucrose. So you had like the dextrose and levo type of molecules, which starts to show that there is some interaction between light and matter in the respect where what you see in all of these experiments is that matter exerts a force in this degree of freedom of light, which is, so matter is changing the polarization of the light beam. So we will try to go filling up this table with our modern understanding of light. And so what I've just described is what is called optical activity, so which is the mechanical effect that atoms can have of light. So atoms can rotate the polarization of light. We know that as optical activity. We know also that atoms can change the linear momentum of light. That's what we call the refraction, the Snell laws. Not good. So I just spilled water here. If there's some towel or something, it will start tripping. You don't see it, but it's on camera. Thank you. Later on, Zeeman and Raman discovered something very interesting, connecting also spin and polarization, which is the following, which is, okay, if you would shine light to a sample and then you would look at the spectrum of that sample, what would happen is if you would put a magnetic field, these lines would shift. And the interesting thing was that there was a strong discussion in that time, which was like around 1930 or so. And you would see, look at these papers written by this guy called Henle and this other guy called Beer. They wrote this paper which is called Over the Anomaly of the Polarization of Raman Scattering, which is written. And very quickly, both Raman and Castor, many people that were around, they're thinking about the theory of quantum optics and what a beam can do to matter, said, okay, this is evidence that actually an atom can absorb angular momentum from a photon and change its internal angular momentum state. So these first experiments where they actually observed that you could actually change the angular momentum of the absorbed or emitting photon were first realized during this time in 1931. But very interestingly, the discussion in physics was a couple of months before. There were not only this paper from Castor, who later received a Nobel Prize on his work on optical pumping. He wrote a paper saying on the non-existence of the spin of a photon. So he was basically saying there's no angular momentum to the photon. 6 months earlier to this other paper where he was saying evidence for the spin of angular momentum of the photon. Of course, the experiment came in the middle, showing that actually you had to account for that. So basically, spinning up this table, we know that in atomic spectroscopy, in the realms of atomic spectroscopy, the energy or linear momentum quality of the beam is seen as different from Hofer lines, and the spin angular momentum was shown by Henle and Beer to change the different absorption and emission curves depending on the incident polarization of the beam. So we can ask them ourselves, what are the mechanical effects on matter? So can light also change how matter is moving and rotating? And of course, the energy, linear momentum, and effects of matter we know very well from Sorry, I got mixed up with what I had in the slides. This we know very well. So the linear momentum and the mechanical effects of matter we know very well from the Kepler comet's tails and from any kind of light pressure. But the question was, okay, can spin angular momentum can also rotate matter? So after these experiments of Henle and Beer came, actually Beth made an experiment a couple of years afterwards, which he was suggested by Einstein actually to do this experiment. And he did a very curious experiment where he had a lamp where he would shine it onto a polarizer, and then he had a very small wave plate there, and light would go by, up and down on this wave plate, and he would show that if he would change the wave plate in one direction or the other one, he could rotate this little torsion pendulum in one direction or the other one, showing that actually this angular momentum of light would actually be translated not only to the angular momentum of an internal electron of an atom, but also to a mechanical object. Many, many years later, Alina Rosenthal, who's a researcher in Australia, demonstrated this with trapped microparticles. So what you see here is a trapped calcite particle, and depending on the angle of the polarization of the beam, you can align it in one direction and another one, or if you put a circular polarized beam, and what you see here are different images taken 4 milliseconds apart, the calcite bead is rotating because of the circular angular momentum of the polarization of the beam. So it's the same experiment, but not with a, well, big, with a small microscopic base. These are microscopic particles, and you can actually make them rotate. So you can physically rotate particles using the spin angular momentum of the photon, using the polarization of the photon. This is something we know for a while. That's back there. This is where this comes. That's why I thought. So of course this little hole here we know from Kepler, we know from the Nichols radiometer, we know from photon recoil, we know from comet tails, beautiful comet tails, we know from the Nichols radiometer, not to be confused with the Brooks radiometer, which runs on another principle. So if you, I don't know if you've seen these radiometers, they don't turn because of pressure, light pressure, but because of one side heating up and heating the air on one side and the other one. Actually, if you think about this radiometer and you try to explain which direction it turns with light pressure, you see it actually turns in the opposite direction. And the reason for it is it's not light pressure when it's moving it. But if you do a very good vacuum in a chamber and you put a torsion balance and you hit one of the sides with light, you see that this torsion balance rotates a bit, and that's what's called the Nichols radiometer. So, of course, nowadays we know we can use optical forces either to trap atoms or to sail satellites and probes into out of our solar system. We use optical forces to move atoms. For example, this is a typical thing, a typical state-of-the-art, well, probably state-of-the-art, 90s or early 2000s state-of-the-art optical clock, where you would start with a laser-cooled group of atoms. You would throw them up in what's called an atomic fountain, and you would probe the interaction time. You would probe the atomic frequency with this very cold, very precise systems, which are actually what are setting the time standards nowadays. So this more or less, we could say by the actually mid-century, mid-20th century, most of all of these interactions were known. So the spin angular momentum of light, we knew how we saw it in atomic spectroscopy, how it could actually exert force on matter, and how matter could exert force on light. So all of the comings and goings of what you could do with light but what about orbital angular momentum? Does light have orbital angular momentum? Actually, nobody thought much about light having orbital angular momentum until sometime in the late 80s where a very nice paper came out, and I will tell you about it in a second. Good. So, but before I do that, I would like to point out that, so for all of what I just said, so if you think of light as a wave, and you think about the wave vector that you need, or the vector potential that you need to describe light or a toroidal field, you can always think that you have, a function which is a slowly varying function of some 3 spatial coordinates. So here it's some cylindrical coordinates. And then you have a part describing the polarization, a part describing the fact that it's a traveling wave, and a part describing the fact that it's oscillating. So the fact that it's oscillating, this is what gives you all of the spectroscopic characteristic. This traveling wave gives you all of the momentum characteristic, and this polarization vector gives you all of the spin or polarization characteristics. So most of what you want. So when you think about non-structured light, you will think about these three terms. But of course, light can have more structure, and that's all in this big, in principle, slowly varying term that comes in front. So I will try to explain you what this, how to think about this term, and what characteristics it has. So first of all, so the wave equation for a complex field, of course, light is not a complex field, it's a real field, but it's easier to work in complex coordinates and then take real or imaginary part as you wish. So we will always have the real fields and the complex fields. The wave equation just looks like a wave equation, which if you just take the assumption that you have a complex oscillating solution, this leads you to the simpler Helmholtz equation, which you can just write like that. So any field that's propagating should be a solution of this equation, but this is normally too general for most of the fields that we know. So most of the fields that we know are mostly traveling in one direction. There's a beam mostly going in one direction, and in the other direction the field will be slowly varying. So we'll be focusing, or it will be turning a bit or so, but most of the field just goes straight forward. So that assumption that the field mostly goes straight forward is what's normally called the paraxial approximation. So we have a field that's oscillating like crazy, and we will have an envelope, we'll be focusing or doing some kind of transformation which will be slow with respect to the variation of lambda. So this, as a reference, I'm taking some of these images and some of these formulas from a very beautiful book that I recommend. It's the Saleh and Teich. It's called the Fundamentals of Photonics or something like that. You'll find it. If you say, okay, I will have a slowly varying envelope, that's envelope I will call A of R, and you have a fast oscillation, which is basically your wave part. You can always write your real field on the following way, right? So the modulus of this part, the complex, the cosine of the frequency t, then the kz, and then you will have some slowly varying phase in here together. So if you take this solution and you go into the Helmholtz equation using the two paraxial assumptions, which is basically, okay, A with the variation of A with respect to Z will be much smaller than K times A, so that's the variation that you have of the sinus part, and also the second derivative will be also much smaller than this. Then you can come to what we call the paraxial approximation, which is basically a wave equation, but in two. So here you have a transverse Laplacian, so that's only the derivative in two directions, and you have this other derivative with respect to Z. Finding the solutions to this Helmholtz equation is not very difficult, and there's actually one thing that you can use as an ansatz. So if you take inspiration from the what's called the paraboloidal or the spherical wave, which is basically a wave that's basically the spherical wave, right? So we have the exponential of k times rho squared divided by z, so 1 over z, a wave that's basically opening as a sphere, but you take this as like the two-dimensional version of that, and you basically replace. Let's say you say, oh, this is a solution of this equation, but let's look for a more general solution where we replace this z coordinate by a function that we don't know, what's a q of z, then we allow this to be z plus some complex part z0. So if you put all of this in the wave equation, you get solutions that have this form. And this form is quite nice. I will step over here to show to you. So you basically have one part that shows you have an envelope, which is a Gaussian envelope. You see it goes like rho, which is the radial coordinate over some waist, which depends on z. You have, of course, the planar wave component, and you have some other terms here. So this term is called the curvature, this term is called the Bowie phase, and this kind of beams are beams that propagate. They have a focus at some point, they have a characteristic which you can call the beam waves, and the beam and the size of the beam evolves through this formula, which is how basically Gaussian beams propagate. From this you can get nice information. So for example, there's a limit at the focus size, which which gives you the Abbe or Helmholtz limit. So the Gaussian is very similar, so this is the limit for a Gaussian beam, which gives you that the smallest size you can have is 2 times lambda pi over d, or pi times theta, where theta is the opening angle. And this is basically what we know as Gaussian beam propagation. So this is going a little bit one step forward in saying, okay, not plane waves, but beams that are Gaussian. It turns out that this, I will skip this. It turns out that this equation, the paraxial equation, has more general solutions, and there are different kinds of general solutions that they have. One of the general solutions that one can find is what we call the Hermite-Gaussian solution. So it's a solution which has the following form. So we have a part which is the Gaussian beam, which is here. This is the Gaussian beam that I just showed. And then you have an extra phase and 2 Hermite functions. The 2 Hermite functions that we know also from quantum mechanics, the Hermite polynomials. If you just do separation of variables into the paraxial equation, you find that this is a reasonable solution. You can do the standard procedure of finding solutions to the equations, and you find that there are some beams that look like this, like the Gaussian beam, or like this is called the Hermite Gaussian 1, 0, 2, 0, 3, 0, depending on the number of nodes they have. And these are stable solutions of the paraxial equation, which means that these beams, if you propagate them, they will always look the same. If you do the same thing, but you do it not for Cartesian coordinates, so if you do this composition of the paraxial equation and you try to find solutions not in Cartesian coordinates but in spherical coordinates, you will find that there are other solutions which we call Laguerre-Gaussian beams. And the Laguerre-Gaussian beams have this shape, so they're donut-like shapes, and they have 2 indices. One, which is which we call the L index, which is the winding number index. I'll show you why in a second it's called winding number. And the other index, which is the P index, which tells you how many zeros you have. You can always also construct these beams. Actually, these 2 bases are 2 complementary bases, like different spin bases or like different positional momentum bases in different dimensions. And you can actually see that the Laguerre-Gaussian beam can be constructed as a superposition of the 2 of the Hermite-Gaussian beams. Here's the formula for the Laguerre-Gaussian beam. And the interesting part it has a very interesting part, which is it has a phase that goes like e to the I L phi. So basically it tells us that the phase is twirling around these beams L times. So here it's twirling no times, here the phase goes from 0 to 2 pi once times, here it goes from 0 to 2 pi and again to 2 pi. So the phase is twirling around them. And almost any phase that's twirling around is a hint of something that's actually rotating. If you look at these beams, so we call this also twisted line. This kind of line is called twisted lines, it's called spiral beams, it's called donut beams. And one of the, as I'm trying to point out, one of the important characteristics comes from these terms here, and that was pointed out. The importance of this term was only pointed out in the late 80s in a paper that was actually that came out in PRA, very long descriptive paper on a proposal of a Gedanken experiment, a thought experiment, where the authors showed that actually this number was accounting for an extra angular momentum that the beam had. So how did this go? Angular momentum of light. So what these people were proposing, these people were Allen, Bergstein, Sproul, and Waterman, and they came with this paper, it was not late 80s, it was early 90s, in 1992. They pointed out that the same way that we know, like in a Bethe experiment, if a photon comes with angular momentum, with the spin angular momentum, polarization angular momentum minus h, and you have a wave plate that turns that into plus h, so a wave plate that turns your polarization from circular right to circular left, then that will impinge an angular momentum on the plate corresponding to the change in angular momentum. And what they asked themselves is, if you actually have a couple of cylindrical lenses, which actually change, and they showed that cylindrical lenses would change this L number of a Laguerre-Gaussian beam from minus L to plus L, they were proposing that this system would actually be able to sense the rotational angular momentum of a beam. But first of all, the first part that they did on this paper, when they actually went to a very small derivation, which I will encourage you to do, but I will just outline here, which is the following. They said, like, okay, what's the angular momentum of a beam? The angular momentum of a beam, m. You can always calculate like r cross the momentum, and the momentum of a beam, of course, is the Poynting vector, right? So you have the Poynting vector cross r cross the Poynting vector should give you the local angular momentum. You can say, okay, we will integrate this over the beam, and that's the total angular momentum, J. And what happens if we say, okay, now let's take a vector potential which has the shape, okay, that's x, it's polarized along x, for example, and it has some shape, and it's traveling along the direction z. If this shape has these funny terms here, which you can recognize from some slides before, so it has, look at this term here, that's the Gaussian term. There are some other funny terms. This is the Laguerre function, and this term here, that's the winding number I was telling you about. If it has a winding number like this, if you carry out this calculation with this beam, which is a Laguerre Gaussian beam, you end up finding that the momentum density has this funny shape here, for a linearly polarized beam. And you see there's one part here that depends on the z coordinate, so there's a part of the angular momentum that's along r, a part of the angular momentum that's along phi, and a part of the angular momentum that's along z. So if you look at the part of the angular momentum that's along z, and if you actually first look at here, so the angular momentum along z, you see it's proportional to L, right? So here there is actually no angular momentum due to the spin. There's no information of the spin in this case. That's for linear polarization. There's no spin angular momentum. But there is an angular momentum associated to L. If you do the same but for circular polarization and you just keep this Z term, you find that there are two terms. There's one term that has the amplitude of the field times L. And there's another term that has the sigma Z now being the polarization, whether it's circular right or circular left. So this sigma Z should be plus 1 or minus 1. So basically what you see here is that the angular momentum along the z direction of such a structured beam has two components. One component, which is the component we always knew about, which is the polarization angular momentum, and another component, which is the orbital angular momentum, a component that has to do only with the fact that you have this special phase here, which is a twirling phase, which actually shows that your phonons are somehow advancing not only with the polarization doing this, but also with the phase doing something like that. And very quickly people turned out to try and show this, and actually the first experiment showing this was Halina's experiment, which is not the one I showed before, but the previous one, where she had a trapped microparticle and she made it rotate by changing the orbital angular momentum of the beam from right to left. And these were the results. This was published in PRL, and you see the particle rotating here, don't you? So I will make a quick vote. I see 4 particles here clearly. 1, 2, 3, 4. Who thinks particle 1 is rotating? Raise their hand.
No, wait, what are the numbers again?
Who thinks particle 2 is rotating? Particle 3? 1, 2, 3, 4. Sorry, go again. So 1, 2, 3, 4. Who thinks particle 1 is rotating? Who thinks particle 2 is rotating? Who thinks particle 3 is rotating? Who thinks particle 4 is rotating? Yeah, it's particle 4 rotating. It's very slightly rotating. But you do see it, right? It's like this one is pointing like this. Somehow like this, somehow like this, somehow like this, somehow like this, and somehow like this. This was the first evidence. It's horrible, but sometimes the first evidence is dirty. I'll show you some videos of things that happened on the following years, and now we have to see the videos. So the first video I showed you, actually, I'm very happy about it because it's a video that's. So this is that's a video of a particle. This was made in the students' lab a couple of weeks ago. With a couple of students came to me. They have an optical tweezer experiment as a students' lab, and they asked me for a faceplate to generate these vortex beams. And I told them, like, I've been asked many times for this faceplate, and many people have tried to make it rotate, and nobody managed. in this student lab in our university. And after, I think, 7 or 8 times of people trying, these people got it. So the fact that sometimes things don't work doesn't mean that they cannot work. Sometimes you have to be thorough. And this is also not the best conditions, so there was low light power, the focusing was not the best. I knew it was a critical experiment to see this, but they do saw that particle rotate. So there was an optical tweezer focusing this light on this. This is a little mushroom, a spore of a mushroom. And with more light, you can actually trap particles on the rim of the beam, as you see there. This is an experiment done at the University of Queensland, and you see that as you trap enough particles so that they actually form a ring, they will start to rotate as the friction is much, much less. This is, again, this video is stolen, as well as the next one. In the next one, what you see is that actually if you change L to minus L, the particles will rotate in one direction or in the other one. Vamos a último. So you see, there the particles are rotating counterclockwise, and now they will change L to the other directions, and they will rotate clockwise. So you can actually turn the directions in which they rotate. So these are much more smaller particles as in the first case. The particles are getting trapped not in the whole beam, but on the bright part of the beam, and you can make them rotate very nicely.
What are the size of the particle?
So in this case, I think these particles were like 100 to 200 nanometer size particles. In the one before, they were like 2 5 micrometer size spores.
What is the size of the central dark zone in the beam?
Here,
More or less.
I don't know very well, but it's something around a couple of microns.
Yeah, okay.
It's optical tweezers micron size. Good. So after the video intermission, we keep on going. So all of those videos were from the University of Southampton. If you look at them, you can Google them, you can YouTube them, they're available if you put orbital angular momentum, Southampton, whatever you find. Good. So basically, can you use orbital angular momentum to move matter? The answer was yes. And what we will do in the next 2 lectures is try to fill in these 2 spots here, but not today. So we will fill a little bit this spot tomorrow, and this one on the following day. How much did I speak?
37.
So I won't skip part 4 then. So a little bit more about beam. So I told you, like, okay, if you do the paraxial approximation and you think, okay, a beam is mostly traveling one direction, you always think that all of your field components are transverse to the direction of propagation. That's what we call a transverse electromagnetic field. And that is normally very nice, unless you start to focus things very tightly. And when you start to focus things very tightly, you start to have components of the field that actually go on the direction of propagation. So you can think about it this very simply. Imagine you have a beam, a very big beam that comes onto a lens, and you have the polarization of the beam, like in this case, this is a special beam that I wrote here. Imagine you have a Hermite Gaussian beam, and the polarization is linear and vertical. As the phase of the beam is different on one side or the other one, the electric field components will be always pointing opposite. What happens when you focus this beam? So if you think of it, the ray that comes here and the ray that comes here of this beam, they will twist a little bit, and of course they will have some forward component. And this forward component will generate some longitudinal component on the center that will interact constructively and will generate some field in the center. This field is normally very small unless you focus close to the diffraction limit, but if you're close to that limit, which is not crazily difficult to achieve, then you will start to have some components in that direction. You can have different situations. Of course, the beam will be oscillating in time and will be pointing one direction and the other one, so you will have a field that's pointing forward and backward, the same way it was pointing up and down. And you can have very, very funny things. So for example, if you actually have, this is taken from another book that I recommend if you want to look at this kind of things. This is the Novotny, The Principles of Nano-Optics. It's a very nice book that goes through a lot of the physics of strongly focused beams. When you see you have, let's look first at these things here. So this is what happens when you focus a linearly polarized beam, so a Gaussian beam. If you focus a linearly polarized Gaussian beam at the focus, mainly if you look at the X polarization component, you will see something like the original. But if you look at the cross polarization components, what you have on the totally opposite component, you see that there's also some light. At the totally opposite, you start with a beam which was Gaussian. It has the same polarization all around the beam, and you focus it, and the different parts of the beam interfere at the focus, generating a polarization which is rotated 90 degrees. It's much smaller, the intensity. You see this image here is multiplied by 252 times to achieve the same gray level, but you still have some component on the opposite polarization. And you also have some component in the propagation direction, that's the Z component here. These plots I'll skip, but there are 2D plots also of the polarization along the focus. And this is already pretty amazing, right? That when you're focusing beams, the polarization scrambles, goes in any direction, and then when they re-expand, things go back to normal. And you can have some funny things. So for example, if you have a Hermite Gaussian beam like this, and you look at what happens if you put linear polarization, as I said, you will have some component in the direction of propagation, but if you have the Hermite Gaussian field now with the polarization in this direction, so horizontal, this was vertical, these, when they focus, they just somehow turn, and there's no wave vector propagating in the direction of propagation, so there's no longitudinal field. So there's some fields that when they focus have strong longitudinal components and some that don't. I will skip this one for a second. You can actually make a lot of very funny beams. So you can make beams that are not uniform, that don't have uniform polarization. So for example, you could think of a beam which has radial polarization. So all along the beam, the polarization is pointing out, or well, on the second cycle it's pointing in and out and in and out. But the polarization is always pointing outwards. You can generate this kind of beams. I showed you in the right-hand side how you generate this beam. You can have beams that have the polarization is always pointing in the azimuthal direction, or always pointing in a spiral turning directions. And this would have very different characteristics when you focus them. And we will see some of the effects of this in the next lectures. So how do you generate, for example, the radial beam? If you have a Hermite beam like this and a Hermite beam like this, so you have a Hermite beam which is horizontal with horizontal polarization, and you superimpose it with a Hermite beam which is vertical lobes with vertical polarization, you get the superposition of these two very clearly generates a beam that looks like that. Whereas you have a beam which is with lobes on the horizontal direction but vertical polarization on the opposite here, then this will generate this kind of things. And then if you combine any of these two, you can actually generate very funny mixtures. These two, the azimuthal and radial beams, are very curious because when you focus them, so when you focus a radial beam, what you see is that there's a very big polarization. So that's a set polarization component. Look at this. This is quite curious. This beam has all in plane polarization, and then you look at the focus and you ask yourself, what is the radial polarization and what is the longitudinal polarization? This beam, as it has all of its vectors pointing out, when you focus the lot, most of these vectors are pointing forward now. So at the focus, most of the polarization is actually longitudinal. So you have a beam that started like a transverse beam, and at the focus it's mainly a longitudinal beam. It still has some radial component, you see? The radial component is still there, but it's smaller. Here it's multiplied by 3, so that you see that same effect. And it has also some, so if you instead of look at the radial component, you look at the y component, you see something like a Hermite beam. If you look at the x component, you will see it in the other direction. This idea is actually kind of curious. If you actually look at this spot here is very small. It's actually much smaller than the beam size, the original beam size, and it was shown by Loix, Dorn and Wavis in 2003 that this actually leads you to stronger focusing that you would expect from the Abel ligand. And they actually showed that, okay, what they had is, so they had a laser that they would pass through a funny way of generating this beam. I won't go into this direction of how they did it. And then they would focus it on a stage where they would have very small light emitters, and they could scan the profile of the beam with these light emitters, and they saw, okay, if they generate a simultaneous polarization, they saw that at the focus with a simultaneous polarization, the beam stays like a donut. But when you put radial polarization at the focus, the beam actually doesn't, if you look at the beam intensity, the beam doesn't look like a donut anymore, and it's very tightly focused. Actually, it's focused actually almost 2 times more than when it would normally be focused just for a Gaussian beam. So this is one nice application. Actually, this was one of the first ideas. This light shaping that is used to do focusing and imaging beyond the diffraction limit. And we will come back to these longitudinal fields, the appearance of these longitudinal fields in the next lecture. So now to finish the last part of today's lecture, it's actually a little bit about also, I will do it also a little bit in a trivia mode so that we relax and have fun a bit. I will tell you a little bit about how to generate this kind of structured beams. There are many ways how to generate these beams, and the easiest, most blunt way of doing it, but sometimes not the best, is the following. Imagine you want to do a Hermite Gauss beam. If you want to do a Hermite Gauss beam, then one very simple thing that you could do is you could have a beam and you would place a glass plate in the middle of the beam and turn this glass plate in such a way that one part of the beam gets delayed with respect to the other one in pi over 2. Why does that work? I will go back to the formula of the beam, but if you look at so you want to generate this beam, and what you see is that the beam on one side and the other side, or on this side of the beam, it basically has a -1 sign. You don't see it explicitly here, but you do see it explicitly here if you actually see, okay, for the 1, the Hermite Gauss 1, this formula goes as 2 times the coordinate, so it's linear on the coordinate, so that shows you that there's a sign change on one side and the other one. So you basically need to change your sign and change your face from one side to the other one. And that's exactly what you can do by just placing a face plate in the middle. The problem is that you're just modifying the face, you're not modifying one of the other characteristics of the beam. You're not modifying the intensity, you're not modifying the fact that in the center there's, in the line in the middle there's null intensity. So what you need to do is you need to filter this beam such that the only component that propagates is the lowest order component. So you go through a lens, a spatial filter, and another more filtering, and you finally get your beam. And that's nice, you can get that. What if you would want to do the Gaussian beams? Okay, you can do Gaussian beams by sending your beam through a spiral face plate. So imagine you have a piece of plastic, glass, something transparent, that optically is thinner, but gets thicker, and then it goes back to. If this optical path is exactly 2 pi, you will actually start increasing the phase, and then go around 2 pi, and then go back to the same one, which is exactly the e to the I phi, with n equal to 1, if that's 2 pi, if it's 4 pi, then it would be L equal to 2, and so on and so forth. You can generate beams this way, but again, you need them to propagate, you need to propagate them, you need to filter them, and so because the light that you have in the middle, so you need a null of light in the middle. And just setting the phase like that won't do that. But if you propagate them enough and you filter them enough, then you will get that. There's a way that I like a lot more because it gets you much better quality beams and can let you do almost anything. And you can do this with programmable spatial light modulators, and you can do them with fixed spatial light modulators, and it's a holography technique. And for that, here we go. So some basic grids. So 101 diffraction physics. So what happens if we hit a beam? So if we hit a diffraction grating, so a grating that transmits or doesn't transmit light like that, we all know that, of course, we will see the interference pattern that somehow looks like this. But what do we see there? Well, there are a couple of things that we see there. Of course, there's the interference that gives us this even spacing, and there's also the diffraction bell that gives us the intensity going down like that to one side and the other one. You can make this better if instead of using an amplitude mask, you use a phase mask. So if this, instead of being the transmission of your grating, if what you have is a phase mask, so something that in terms of beam paths looks like a sawtooth, like this. You see, it's like the beam path increases, and then decreases, increases, and decreases, increases, and then decreases. If you do that, you can actually move your diffraction bell to one side or to the other one, and you can, for example, make the first, or if you move it to the other side, the minus 1 order of diffraction the most intense. This is what we call blaze. And you can do blaze in order to put up to 90% of your power onto the first order of diffraction. So you can diffract very well if you hit your blaze correctly. Now, so the idea will be, how can we use these two ideas now to generate the fact that this diffracted beam will now be either a Hermite Gaussian or a Laguerre Gaussian beam. And you will, this looks like an optical trick to get you dizzy, right? I didn't realize on the computer when I was doing it, but if you look at it, it's like, is this line straight or not? It's not about that. So what would happen if you actually do a diffraction pattern like this? What do you expect at the output? So the diffraction rating at the top is the same as the bottom. The spacing has to be the same. But what changes? I just place one with respect to the other one. What do you expect to have?
If they shift, they're like two in each other?
It will be exactly a phase shift with the top part with respect to the bottom part. And you have a discrete phase shift on the top with respect to the bottom, and that phase shift, because of the symmetry, we could say it should be pi, it should be a -1. What beam would you expect to get diffracted? A Hermite Gaussian beam. And if you do this, you actually have, in your diffraction patterns, you see, so if you have a grating that looks like this, what you have in the end is exactly this. So the first order looks like the Hermite Gaussian 1, 0, the second order 2, 0, and then the other ones like that. If you on top of this do a blaze, you can eliminate most of these orders and just have one of them. So, given this, what would you do to generate a circular beam? Yeah, somehow like that. You wanted, this would generate a circular beam. And what you see here, you see the top and the bottom parts are displaced, but they're halfway displaced, and the middle part, if you look at it far away, it's quarter way displaced, and this one here is quarter way displaced. So it's basically somehow your phase pattern is slowly displacing around the center where the beam propagates. If you do this, you get this very nice beam. So you have the Gaussian 1 and -1 to one side and the other one, 2 and -2, and continue in the orders. And this is a very nice way of generating beams, and the nice thing about it is that you don't need to filter them afterwards. The beams that you get at the output pretty much look like this. They don't look exactly like this, and you will see evidence of that in the next slide. They actually have loads on the side. So if you, I will go back a lot. Just a second. On the first order, you have a mixture of this one and this one and this one and this one. And the second order, you have a mixture of this ones. So you have a mixture of the p orders because that's if the phase that you put is just like this. You can also decide to modulate the amplitude. So using the phase pattern, you can also decide, okay, I will try not to diffract so much light from the center, so I will do the phase contrast here less and bigger on the side. And you can actually do that with a very simple holography principle, which is the following. So I will now go to very simply use this. So the simple holography principle is the following. So you have your beam, and you have your have, and you have your want. The question is, what do you put here to get this thing? And you say, like, okay, if want was coming from here, I calculate the interference from have plus want. I calculate what would be the phase pattern here, what would be the intensity and phase pattern at that plane, and then I generate a mask which has exactly that same plane. In such a way that if I only have will no interference with the phase and amplitude information that I need in order so that what you get diffracted is your want beam. That's a basic holography process. And in principle, to do a perfect holography, you need to have a substrate that can do amplitude and phase. And many times you cannot do amplitude and phase, many times you can only do amplitude, or many times you can only do phase. And curiously, it works very well if you just do one or the other one. You just have either less efficiency or so, and you can always correct, and you can actually adaptively correct to get a very good diffraction, almost perfect diffraction of what you want, even if you only have amplitude or phase modulation. In fact, I would like to point you out to a recent result which I like a lot, which is by Joel Carpenter, who's also an Australian researcher, who found out a very nice way of finding optimal transformation of any beam to any other beam with multiple phase planes. So if you have 1, 2, 3, 4, in this case 5, or a couple of phase planes, you can transform any mode into any other spatial mode that you want by doing an extension of this holography principle, which is, you say, okay, I have, let's say, my beam is coming from this direction and going in this direction. And what I do is I propagate from this back direction whichever beams I want, and I propagate from the forward direction whichever beams I have, and I try to match them in the different planes, and I do that iteratively, and you can, doing this, then you can actually match whichever beam you want into whichever other beam. And this was a long-standing question, actually, in the use of this kind of spatial structured light beams for quantum or classical communications, where you would store in these degrees of freedoms of these beams, again, quantum or classical information, and you would want to sort them at the end. So the same way you want to, when you do communications, you want to sort frequencies, or you want to sort polarizations, you would want to sort different shapes of beams, and you can actually do that by using this extension of the holography principle, which was developed by Joel Carpenter. So, that said, and as this is a school, if you want, if you feel like it, here are some exercises, which are basically going through some of the things that I showed today. None of them are very difficult, and I think they're nice things to sit down and do once if you're into this kind of stuff. So calculate the Gaussian solution of the paraxial equation using the spherical wave ansatz, which is basically going through those steps that I can do. Also show that Hermite and Laguerre Gaussian solutions are also solutions of the same of the Helmholtz equation. Go through the derivation of the formula of the total angular momentum of the Laguerre Gaussian beam. I think that's a beautiful derivation that you can at least read through in the paper with a half hour or an hour of quiet time. And this last one, calculate the hologram needed to generate a Laguerre Gaussian beam using purely a phase equation. So that's all for today. And if you have any questions, let's talk a while, and if not, after. Thank you very much.
Question? Okay, I came all the way here, so please question. don't waste my energy.
Where do we go to here?
Hey, Christian. Thank you very much. Is there any relationship? So typically, when you think of a beam, you wouldn't typically think of polarization that is longitudinal, right? And that you can get that from the pointing vector and so on. Is there any relationship then between this excess longitudinal polarization that you can get for these beams and how tightly you can focus? Is that related to sort of K parameters and so on at the focus point?
So I don't know if there's a like one-to-one easy formula relationship, but there's definitely a collection of beams where you can say these beams where you can intuitively say they will get tighter focus, and this one's not. It's kind of clear to me that the ones that have strong longitudinal polarization get stronger focus than the ones that don't, and then in that sense, as I showed, there's two very clear strong examples. You have the asymptotically polarized beam, which doesn't get compressed at all, and you have the radial one that gets very well compressed. Then you have all of the other combinations, and the things that happen with all of the other combinations is like whenever you choose the wrong alien basis to discuss your physics. You have like a mixture of, okay, gets well focused in one direction, but not so well focused in the other direction, and yes. So I would say that probably the best answer is you can tell that the best possible focus beam is the radially polarized one, and the worst one is the azimuthal one. And all of the other things you can make as combinations of those.
Can I ask? There is a slide that you show us, which intensity interference pattern with some four different beam. You can show again, please. So my question, this, thank you. So my question is, why increase the size of the OAM value? Because I saw the same mass. So this is the question.
Yeah. So there are two answers to the question. So I don't know if the question is why is the radius of this bigger? The radius is because it's bigger because it has more angular momentum. The question is why does it have more angular momentum?
Yeah, because I saw just one mass.
Good. It's only one mass. So the thing is, if you look at your different diffraction orders, always your first diffraction order is like the first time you interfere like this part with this part, and your second diffraction order is actually this part with this part. And the same thing. So the same thing happens when if you calculate the interference of one and the other one, you see that you actually have to go 2 times. You go more times around spiraling the phase. You can count it here. I'll just show you the first one, but actually if you just go around and you say, okay, how many times do I go up and down from white to black from this to back to here, and then in the other case you would say, okay, how many times do I go up and down if I have to go from here to here? You basically see that
Okay, I see.
that you go more times around by.
Thank you.
Is there a quantum uncertainty principle associated to how much I can focus a laser beam?
Okay. So the obvious question is yes. The obvious answer is yes. The question is how.
Yes, what is the complementary
So
circle?
the complementary to the size is the k vectors, and that's like how when you have. So if you have a very tightly, it's very easy. So if you have a very tightly focused beams, that beam is composed by many k vectors. You have, let me just. But this doesn't even. It's not a quantum complementary. It's a wave complementary effect. Let me just use this as a illustrative. So you see, this beam has this k vector, has this opposite k vector, has the zero k vector, has one of these ones, and it will be very tightly focused here. A beam that is not very tightly focused, which is much bigger, has all of the k vectors are mostly the same. So k is very well defined, x is not so well defined. Same thing.
All right, thanks.
I'm curious, is there a way to quickly switch between these beams? So, for instance, you showed that you can use an SLM to kind of transform beams arbitrarily into these orbital angular momentum beams, but is there a way to go faster, let's say microsecond scale?
Yes, but you need to combine techniques that allow you to do that. So I don't know of any purely holographic technique that goes faster, but there's always combination of either using an AOM or ARD or electro-optic deflector and a fixed diffraction pattern. So you can switch between turning on one or another beam that you have fixed on. It's the same kind of problem that that people with working with neutral atoms have in doing these optical arrays. You can define an optical array that you can change with your SLM if you're very good in milliseconds time, but if you want to move things, you need to use electro-optics, and because SLMs won't do it. And of course, you can have the easiest thing that you can do is if you want to switch between two things, you just have an SLM with the two diffraction patterns that you want, and you hit one or you hit the other one, and you just turn on and off the beam with an AOM. But I don't know any other like native way. If you happen to know, you have any ideas, I think that would be a piece of technology that would change not only the interaction of structured light with the atom, but I think quantum optics as a technology platform.
Thank you.
Imagine that you have the following. Okay? So you have a magnetic conversion, you have two photons, and you put these two photons in different spheres, so that they have different angular momentum. But it will happen if you recombine them.
So I didn't quite understand that. I understood a little bit of the question, but I can probably answer you something on the side. So there was one of the first experiments that came out after this whole craziness of orbital angular momentum started was an experiment done by Seidinger's group, where they actually showed that if you have twin photons generated by a Gaussian beam, but if you filter them, looking at what's the angular momentum content of one and what's the angular momentum content of the other one, if they're generated in an indistinguishable way, they will always have equal and opposite angular momentum. And that's kind of reasonable because the photon originally didn't have angular momentum, so if one has +1, the other one has to have -1, and you actually have a belt state of these two, and they measured Bayes inequalities between these two.
If you want to make them do interference, having different angular momentum, so I have this twin photon, okay, that obviously they have angular momentum has to be orbital, or and has to be zero because they can the same magnitude. But now if I put this one to a plate, another one with another plate, do I have
OM1 with OM2, for instance, and then I make them to interference between them, what will happen? What I will see?
So if we are talking about two photon interference,
yes, but that they come from identical.
Yeah,
originally they were-
so you will break totally the interference. The same way as it happens with polarization. So if you have two photons generated together, twin photons, exactly twin photons, you get them together at the beam splitter, you have conformal interference, which means the two of them will go together in one direction or in the other direction, but they will never reflect one to one side of the one. However, if in that experiment you rotate the polarization of one of them and you make them interfere, you will see that you have all possibilities. It's just a random particle just bouncing on that beam splitter, no quantum interference. What will happen if you do the same thing with angular momentum? I think this experiment has not been done, but I will bet all my money that the same thing with polarization. Because it's just another degree of freedom, it just identifies one path with the other one, and that breaks interference.
If I can say, in our laboratory we have done that.
Great, you see?
And there is a pointer that everyone missed at the moment. It was that if the two angular momentum are opposite, they do interfere, because in the beam splitter there is the reflection on top of the two. But if you put together the two with the same angular momentum, then the interference is completely lost.
There you go. So you need a special reflection.
You will have lost money.
Okay, any more questions? If not, let's thank Christian again.